Oh, there we are. All right. Thank you, everybody, for joining us. So this is a panel to talk about the impact of chiplets and heterogeneous integration and modularity on AI and HPC systems. And this is part of the server and open chiplet economy effort. And this is just the general gist of our panel here is that chiplets, they're discrete components, dialects really, with specialized functions, and they're reshaping system architectures by enabling integration that goes beyond the reticle limit. Oops. Okay, and that we can partition up into modular components into these chiplets and co-integrate with high bandwidth between those chiplets in order to create a variety of modular functionalities with a handful of different masks and chiplets. So we're going to have a distinguished set of panelists here who are going to attack this from all the different angles. And since we have an hour here, let's just dive right into it. And we're going to bring up our first panelist here. Oops, what's going on? There we go. Prith Banerjee, who's Chief Technology Officer for Ansys. Okay, I think this is on. There you go.
Thank you, John.
Thanks.
So thank you very much, John. So as John mentioned, I'm CTO at Ansys, but I have worked in the area of HPC for a while. I started my career in academia. For the first 20 years, I was at University of Illinois and Northwestern. And then the last 15 years, I've worked in the corporate world as head of HP Labs, CTO at ABB, Schneider Electric, and now at Ansys. So who is Ansys? So Ansys is a leading CAE simulation tool provider. So we take the world of physics around us, which is structural physics. We solve it through finite element analysis, fluids physics with Fluent, with finite volume methods, electromagnetics physics, which is Maxwell's equations. So we take Euler's equations, Navier-Stokes equations, and Maxwell's equations, and we solve them numerically, and circuits and so on, right? These things are very accurate, but they take a long time. Just to give you an idea, you look at all the HPC workloads on the cloud, 35% of the HPC workload on the cloud is CAE simulation, running finite element methods for structures, etc. So that's kind of the world we live in. And our things are incredibly accurate, but they take a long time to run. And therefore, my pitch here is, how do we use these simulation tools? Two things. How can they be accelerated, improved upon by the technology of HPC and AI using chiplets? And that is actually the work that I do a lot in my world as CTO. I have these 5 technology pillars, and we have work on AI, ML, using AI to train those AI models. And once you train them, instead of taking 1,000 hours to run, Ansys mechanical, it'll run in an hour, right? So it's literally hundreds of times speed ups powered by GPUs and all that kind of stuff. We also use brute force HPC, means you take a piece of code and run it on shared memory, message passing, GPUs, all the stuff. So all our solvers I talked about run on HPC. But then just the previous speaker kind of talked about sort of a special purpose accelerator, right? So we have been exploring, right? Could we take this Fluent code and yes, we can run it on a GPU, but if we had that specific thing to accelerate the finite volume methods of this thing, it could be even better. So that's the first thing which is not on this slide, but there is a lot of stuff that we do on using HPC and AI technology to accelerate our solvers. And that today we do with general purpose HPC and general purpose AI, but using chiplets, you could actually do customized special purpose accelerators, as was just mentioned by the speaker from LBL. The second contribution that I want to talk about, and then I have a slide on this, is how using simulation, you can actually advance the work on chiplets, right? So I mean, what are chiplet? Basically, in the previous slide, right, people talked about printed circuit boards. So on a printed circuit board, you have chip number 1, you have chip number 2, and they're connected through whatever, right? So with today's technologies, with Ansys, you can model the power thing in a chip, right? And you say, okay, with Red Hawk SC, we can say how much power will be distributed, what are the power drops and power integrity. Then you can say, depending on that chip, it will generate this much power, like 2,000 watts, so it will heat up the printed circuit board. So what's the thermal behavior, right? So we model it through Ansys mechanical. Then because of the thermal, things expand, and you create mechanical stresses. We model that through structural. Then we say, now you have to cool this printed circuit board. How do you cool it? Well, with air cooling or water cooling, there's all kinds of stuff on liquid cooling in data centers that people talk about. You can model it all through Fluent. So in the world of chiplets, you take all these different components and you put it on a chip, right, with those high-speed interconnects, right? And now you're dealing with technologies which is essentially saying that I have to do structural integrity. All these different chiplets that you put, right, and you put it together using all those interconnects, right, you will have structural stresses in there. Can I simulate and can I sign off that, yes, this thing is going to work? That's structural integrity. Power integrity is saying that in these billions of transistors, there's 200 billion transistors, and you put 5 chips like this, right? It's going to generate, is 2? Okay. So that is power integrity. Then you do signal integrity. You have all the EMI, EMC interconnections, right? And so can you verify that? So essentially, we have taken a world, a view, where you can take these complex chiplets do sign off for power integrity, signal integrity, thermal integrity, and structural integrity. And then using that, what can you do? You can do amazing things like co-design, right? So think of Lego blocks. Yeah, I take this system, so on, right? Now, it turns out that suppose you are putting a chiplet on top of another chiplet, and the same vertical direction, you have a lot of heat being generated, then this thing in the middle is going to be super hot, and all kinds of bad things will happen. So if you can analyze it, you can say, hey, let me move things around on that chiplet so that simultaneously 2 things are not hot in the same vertical direction. So essentially, we are using simulation as a way to do all these integrities across this thing. So that's sort of my pitch. Thank you very much.
All right. Under time and under budget. All right. All right. Oh, let me. Guess I located ourselves on the wrong side here. We have to take the long way around to get up on stage. Okay, so so next up we have Bill Chen from ASE. And he also leads the Heterogeneous Integration Roadmap effort, which is up around 800 pages of very useful information at this point in time. So, Bill? I'll hand you the mic here.
Thank you. As John mentioned, I spent a number of years in IBM, and then I went and spent some time in Singapore on a research institute. Then I came back to US and started working for ASE. And when I worked for ASE, at the time, I was also part of the ITRS, International Technology Roadmap for Semiconductors. And when ITRS came into a close, and I was in the packaging technical working group, and also a part of the heterogeneous integration functional team. And we decided that we cannot let the effort in heterogeneous integration slide. So we went around went to the Electronic Packaging Society, Electronic Devices Society, Photonics Society, SEMI, and said, we like to continue this effort. We think it's very important that this heterogeneous integration will continue to continue to flourish, work on in our industry. And I was fortunate to work for a company that said, this is important for the industry, and please spend as much time as you can on this. So that is how I continue to work on the roadmap. At the same time, I also brought together a very dedicated group of volunteers to make this roadmap continue to flourish. So I'm going to talk about heterogeneous integration in this AI era for the simple reason that it seems to me all the different developments are coming into being. First of all, how do we advance this?
Did it go blanket there?
No, on the laptop.
On the laptop?
Arrow sign.
Yeah, arrow.
Arrow sign on the laptop.
Can you just show me this one? Nothing happens.
Oh. Just click.
Now we go. Okay.
Ah.
So at the same time, we have a tremendous amount of change in our industry because the CHIP Act has come around, the CHIP and Science Act. And now we ask our question, what is the chip and what is the science? So the package, now it becomes the chip. We talk about chiplets. The chiplets is the package, and the package is the chip. Now, what we are going to ask ourselves, what are the packaging sciences? You can see the good example of this package and what lies between the science that has been utilized to build this simple, I shouldn't say simple, to build this chiplet package. And how do we count the waste of the science that goes into this? Our previous speaker spoke so much. He believes in the modeling, simulation. The science goes into the whole thing because modeling is based upon science. And what we are seeing today is the convergence of AI that brings the science together into a generative AI, and there we are going forward. So heterogeneous integration roadmap, when we designed this roadmap, we said that we want to start with a system approach, high-performance computing, mobile, medical health, automotive, IoT, aerospace, and defense. And then we have the components of the heterogeneous integration in terms of advanced manufacturing and multi-chip integration, including substrates, of course, photonics, power integration, MEMS and sensors, 5G, and beyond. Then we have cutting topics, such as materials and emerging materials, test, supply chain, security, thermal management, and reliability. Then we have some three groups which people think about as advanced packaging. That is 2D and 3D and interconnect, SiP and modules, wafer level packaging, fan in and fan out, and of course, most important are the two next one, co-design and simulation. So we have these 23 technical working groups, each staff, when I say staff, wrong word, volunteers. And they are composed of what our ecosystem together. All of us together are part of this total ecosystem. Oh, yes, I also want to say that we have a chapter on additive manufacturing. It's pending to be released. I shouldn't say, it's ready. It's just that we need a final readout. So Chiplets is heterogeneous integration in its very, very important form today. And you could see that we look at this from the point of view as a large multi-chip module, 2D and 3D, fan out. Now we are looking at it in terms of hybrid bonding. These are the technologies that goes into it. And then we look at it and say, what do we see as a future? Fortunately, we have a slide from Eric Ban at the Semicon West. He showed us that how are we going to look at the 3D interconnect. And this would be, it's a very good way to look at how are we going to the future from a final pitch into 3D systems. So semiconductors. Our friend from TSMC, he looked at it and said 2030, GDP will be at 145 trillion, and he see that semiconductors, chiplets, is going to be an important foundation for us to create this global economy. And so the package is the chip, and the science is the packaging science. And what are the packaging sciences we all need to bring together so that we will create this 145 trillion GDP economy? That is all I have. Thank you very much.
Thank you. All right, so let's see here. So next up, we have David Ditzel, who's from Esperanto Technologies, and he's going to try out. Are you going to do this? Are you going to go to the other side? Okay. All right. No.
Hey. Okay, hey, thanks very much. It's a privilege to be here today. I'm mainly here to just offer support kind of for the chiplet vision. Just for my bona fides a little bit, I've been designing high-performance CPUs for over 40 years. I helped get, maybe you may know what a RISC microprocessor is. Professor Dave Patterson, my professor, and I wrote the first paper called The Case for RISC back in 1980, and I've been building RISC CPUs ever since. 10 years at Bell Labs, 10 years at Sun Microsystems. I was CTO for the Spark processor business. Then I founded a company called Transmeta that did low-power x86 CPUs and really changed the direction that Intel and AMD had to take because they were going in a direction of increasing power. Now, think of that. If they hadn't gone for low-power chips, where would we be today, given the power of chips is now in the half-kilowatt kind of levels for CPUs, and AI chips much more than that. I then went to work for Intel for a while. It was one of the few companies I hadn't worked with to understand really what was unique about what they had done, and tried to bring much more efficient processing to them, but it's a big company and that's a challenge. So at some point I realized to be in control of my own destiny, I was better off at a smaller company. So I started Esperanto Technologies. And what we pioneered at Esperanto is utilizing the RISC-V instruction set. And we put over 1,000 general-purpose 64-bit cores on a single chip. So we pioneered how much you could squeeze onto one chip. And then the future is going to be chiplets. So with over 1,000 on a chip in 7 nanometer, we're going to take this future into chiplets where we're putting together multiple chiplets to put several thousand cores in a little module. And Bill is absolutely right. The future is packaging here for where we're going. So I just want to make a couple simple comments and then maybe whine a little bit about the current situation here. So first of all, I'm absolutely a believer in chiplets here, right? Chiplets are going to be found in almost all of the high-performance computing systems in the future. It's really inevitable. It's a way to cut down the amount of power in communicating between chips. To put things in a package, you can save a factor of 10x or more in I/O power. And as we need to get to lots of memory and have lots of bandwidth, you would just have an unaffordable amount of power if you were not to go to a chiplet-based approach. Now, although I say you'll see lots and lots of chiplets, the reality of chiplets today is that the successful chiplet solutions are all almost entirely done by a single company, basically building all the chiplets themselves. If you look at an Apple or AMD or Intel, they've all got chiplet-based solutions, but they do their own chiplets themselves here. And that's because that's one of the only ways to really guarantee that the chiplets will interoperate. So longer term, I do believe that the industry is doing good things towards interoperability. I've seen many of the chiplet presentations today. And if you look just by the large number of people and teams they're putting together to try and solve this problem, what you have to realize is it is a huge problem. We are nowhere near the ability of having little Lego blocks that all just plug together, right? And so I guess what I would say is that a lot of the standards being put together, they are not yet at the point of enabling this easy interoperability here. What we have is really amazing slideware, right? But most of that slideware does not contemplate the reality because our imaginations run wild with the possibility. Well, imagine, putting just, you've seen the pictures, 10 little chiplets together here. Oh, let's put them all in 2 nanometer technology. Well, think about it. What does it cost to tape out 10 different chiplets, right? That's $250 million in mass costs, right? So it's not going to happen that way. So you've got to have some really very compelling solutions in order to do that. So it'll be smaller number of chiplets or identical kinds of chiplets. So for example, Esperanto, we're on a path to use chiplets, but the way we make it work with large numbers of chiplets is we make our own chiplets talk to each other, right? So that's the simple way of doing that. We looked at trying to just acquire chiplets from different chiplet vendors that we saw being announced. And every time we went to a chiplet vendor and we came in, it was like, oh, it doesn't quite work because of this problem. Well, we have different pad pitches. We all talk about having UCIe interfaces. Well, that's really great. You've got a common plug. It's like having 110-volt plugs in the US, but you've got to have the right protocol behind it. If somebody's running DC and someone else is running AC, the fact that physically you can plug things together doesn't necessarily make things work. So there's just a lot of issues to solve. I think it's a great thing to work on, but beware that as you get involved in this, there are a lot of things that yet have to be standardized and worked on together, and so I want to encourage this community, keep working on it. We'd love to get to a future where we can connect things together, but it's going to be one that's going to happen over the course probably of the next 10 years or so, not something that in the course of 1 year you're going to be able to go to a chiplet marketplace and just order out of a catalog of lots of chips and put them together. Certainly not with things with very advanced technology. If you use older technologies, you go back to maybe 45 nanometer older and a smaller number of things, yes, you could put it together, but is there really a market for that? So a lot of things have to come together for this to happen. So expect to see lots of interesting things changing in the future here. But we know that chiplets is the way to go. Thank you.
Let's get it this way.
I'll walk off the proper way.
Yes. All right. Yeah, we don't want to kill our panelists, at least not before they get to sit up here. All right, so next up we have Ramin. Farjadrad. I didn't practice pronouncing people's names before this, but I'll meet you over here. Right. It would have
being
been nice.
efficient.
Yeah.
So good afternoon, ladies and gentlemen. I've been, just a little bit background on me, I've been designing wireline transceivers for most of my life, for almost 30 years. Back in the 90s, I started working on maybe some of the first CMOS multi-gig SerDes, which we call it today SerDes. And this is kind of like a name that came up afterwards. The 5 gig SerDes and also the first PAM4 SerDes that at the time I proposed it to be able to build 10 gig link at a very, let's say almost half a micron technology. And that enabled us to run at half speed and also help with the interconnect. And of course, using SerDes in CMOS had a lot of benefits. The first company I did, Velia Communications, managed to put a couple of hundred of them on a single chip and get close to almost a terabit per second in a single chip on a switch fabric, so which was new at the time. And also did some more work, expanding the work on the PHY in CMOS, different Ethernet PHYs, 10G-based T-PHY, and also around 2010, 2012, we noticed that wireless access points are going beyond 1 gig, which was the old installed base in the day. Enterprise was at 1 gig, which was a shame. Usually wireline, but it's run faster than wireless. So I came up with a new PHY technology, multi-gig Ethernet for enterprise that expanded the bandwidth over the same cable infrastructure up to 5 gig, that turned into an IEEE standard, and then followed by somewhat similar technology, but also using PAM4 simultaneous bidirectional for automotive Ethernet. That also became IEEE standard. But the focus of my current company, Eliyan, is something that started in my last company. We were supposed to compete with the likes of Broadcom on the PHY side. And of course, one of the advantages for the PHY was being low power, high performance. When people moved into FinFET, 16 nanometer, 14 nanometer, the mass cost was high, not 20, 25 million. And Dave said back then maybe it was 4 or 5 million, but still, we had 10 different products. Wanted to do all 10 of them would be $50 million. But the reality of it was the components for this products we had was mainly built of PHY, a controller, and a switch. So back then I started, it was 2015, 2016, the idea of using chiplet architectures, have different tape outs, only 3 tape outs for this, different pieces, and then connect them in different shape or form to build the 10 different products that we had. And it worked beautifully. And one of the key parts for it was that we actually needed a very efficient die-to-die interconnect. And back then, by efficient meaning high bandwidth and very low power, low area. And back then there was no, let's say, advanced interconnect technology. So that's what drove me to kind of start thinking how we can manage to, actually, maybe the order this way, how we can manage to get really high bandwidth as if these chiplets are all sitting on a single chip and talking to each other, also low power. And that technology, I took it into Eliyan. And we were able to drive it in the last 2.5 years to all the way to 64 gigabit per second on a single wire, on a single bump at a very low power. And this technology is something that you can use it in a standard package. It still gets all the way up to 5 terabits per millimeter. And by standard package, I mean something that is, the bump pitch is more than 90 micron. I guess more commonplace today is 110, but 90 micron is considered standard. But also can be applicable to advanced package. When you apply it to advanced package, we can go all the way up to 20 terabits per millimeter, and even lower power, like under 0.3 picojoule per bit. And this is something that we have in silicon 3 nanometer chip that latest came up. And one of the key advantages of being able to get this much bandwidth on a standard substrate is that you can build large, interesting AI or HPC solutions without having to have really large advanced package substrate. For example, Blackwell, more recently, uses like a 3.5x reticle, as you see in the picture. And the larger it grows, the size of these advanced packages, they'll have yield issues, which I'll talk about in my next talk. But if you can limit the number of chiplets that you put on them, you can reduce the size. For example, we can go to a solution which is twice as big as Blackwell with 4 reticle size chips and effectively 16 of these HBMs are on it, but with even smaller reticle size, as you can see in the package over there. Because we can provide with this technology the bandwidth of an HBM4, HBM4E up to 20 terabits per second between the chips, just using standard packaging that beachfront. So this is one of the advantages. And of course, we don't want to be a company that has a proprietary technology. So we are careful to basically propose it in different standards. We propose it at JEDEC, to standards at JEDEC as SPHBM, and also at OCP UMI. But okay. But the other key advantage and things that we've been promoting in the industry since 4 years ago is using a FinFET base type for these HBM, so we can do more things. And one of the key things we can do with it is building a multi-port HBM. And once you do that, you can do a lot of interesting things, as you can see. For example, on the left side, I don't know if you see the mouse here, you can daisy chain HBMs and expand the amount of HBM and effective bandwidth there. I don't know why this is moving. Or you can connect it to, LPDDR and get even more bandwidth and more capacity through the other side of it. Or usually today, when you put this HBM across one edge of a processor, effectively this edge is not usable anymore. It's a waste. But given that you can get a lot of bandwidth through that beachfront, you can pass the excess bandwidth to the other side and use it for SerDes communication externally. So rather than going to 200 gig SerDes to get the extended bandwidth, you can use all 4 edges and stay at 100 gig. Or if you have 200 gig today, rather than waiting for a 480 gig SerDes to come out, you can use the 200 gig SerDes and get the double bandwidth, in fact, more than double bandwidth this way. So this way, combination of these solutions, you can basically break the memory wall and I/O wall, which are the 2 main bottlenecks for the AI chips today. Thank you.
Great. Thank you, sir. All right. And so last but not least is, and now this is where I forgot to ask, Francesc. Okay. Guim, talk about the European Union.
Good, thank you. So I go by Cesc. Thanks for the intro. So I'm the CEO of Openchip. Openchip is an European company that is based out of Barcelona, and basically our focus is to develop HPC and AI accelerators. In this context, in the past, I've been working like more than 20 years at Intel. I did my PhD before at BSc, so I know the area quite well. And I think one of the interesting aspects that I've seen like recently, it's when I did my PhD, most of the workloads were FFT-based or stuff like that. And now as you see how the workloads for HPC have evolved, like the combination of AI and traditional workloads is becoming more and more prevalent. So a little bit what we're trying to do in Openchip is try to see how we can architect AI and accelerators, but also that they have vector capabilities, which is a fundamental aspect from HPC workloads. The company, as I said, is based out of Barcelona, but we have sites in Italy, Ireland, and in Germany. So something important about the work that we are doing, I think I like because the panelists talked a lot about system, right? And at the end of the day, like when you talk to the end customers, who cares about hardware? They care about the functionalities and what the system provides. So a lot of the work that we are doing from that side of things is looking at the SoC architecture, combining the chiplet technology, but looking at that from the system perspective and how the system is being utilized by the applications, right? And this is guiding us a little bit when you understand the different workloads that you have, how basically what technologies that do you need and who do you have to team with to kind of connect the right level of accelerators or compute or whatnot. In this, and there's another interesting aspect. So our accelerators are based on RISC-V. And I think typically, and I was at Intel before, and when you are bound into legacy ISA and everything very static, it's difficult to kind of add new functionalities. So one of the beauties of combining a little bit chiplets plus RISC-V is that now you can develop new hardware APIs, and that means that you can do a much more interesting hardware and software co-design. And in this case, so from our side, so I mean, you have to pick and choose your battles. So we want to do, I mean, we would like to do everything within the accelerator for HPC, but the reality is that, I mean, if you want to reduce the time to market and the go to market, you need to find your partners, right? And basically focus on the areas where you can add value. And in this case, Chiplets is helping us out to kind of reduce risk and go and the go to market. However, and that's what I think that there is a lot of work that has to be done. I mean, they've said about the slides, right? And I kind of agree. We need to do stuff around maybe attestation, right? So once you are connecting different components that you have not designed, how you establish trust around those different components. How do you do validation and attestation? So one thing is when you have your own technology, and you do a monolithic system, how you validate those elements that all together, right? Because in many cases, chiplet is just a piece of silicon that you integrate to do a final product. So how you provide the level of reliability that the customers are expecting. And I think the other important aspect is on the interplay on the different parts of the stack. So I'm part of the RBI board and there is 5 standardization body. And basically one of the things that I was mentioning the other day is that we should connect OCP with what is being done on RBI, because at the end of the day, you need to connect all the pieces consistency. And finally, I mean, connected to the standardization, right? So again, when you look at the technology from system perspective, you need to do power management. You need to do telemetry. You need to do a bunch of things that relate to manage the SoC. So now if you have different implementations of the chiplet, that they have different personalities, different ways to do those things, how you manage that from software perspective or even from the hardware, right? So I think that there is a lot of work that we need to do as ecosystem on how these things work together in a cohesive way, but as well how that's managed from the software perspective. So I think that this is, I mean, in my opinion, chiplets, it's a must, but there's some work to be done. Thank you.
All right, so let's have our panelists come back up on stage here, and I'm going to cede the 2-minute card to Anu. And since we're on time, we actually have plenty of time for messages. Yep. Yeah. Anything's fine here? Yeah. Oh, you're going to try to match up with the thing above you. All right. Very, very organized engineers here. All right. There you go. All right. Engineering solution. All right, so do we have any questions from the audience here? Please, if not, I'll, yeah, come on up. Yeah, I've got questions queued up if you don't, so. Come on.
Hi.
Hi.
There was some discussion around kind of production silos making chiplets that are theoretically a modular solution. Well, if everybody has their own specifications for that modular solution, it's not really modular. If you were to prioritize a design characteristic for adopting a standard, right? If you were to say this is the one that's most likely to be a barrier to compatibility, that could be, you know, materials, it could be thermal properties. What would you prioritize?
I would say the interconnect would be number one, because at the end of the day, people who want to connect these chiplets together, they have to make sure that these chiplets can talk to each other properly, smoothly, and without any hiccups. And making sure that we get these interconnects standardized is key. But unfortunately, the only one that has been successful maybe has been the HBI for HBM. That has been the standard. People have been using different vendors. But as Dave mentioned, everything else, people try to do it internally because I would say not necessarily, because it's not possible to have these standards like UCI or BOW, but sometimes it's more of an economic reason or like say business reasons that companies that, let's say, do the ASIC, they say, oh, I have to provide both D2D on both sides, otherwise I cannot guarantee that they work. And they create this fear that, just to secure the business aspect of this. But making sure that these files can interoperate with themselves is not a big deal. It has been done. HBI is an example of it. It's just that industry needs to mature, and people need to understand they don't have the fear of what if it doesn't work and the push for it.
I'd like to add on top of that, I think he's right that the physical interface is the first thing we think about, and then we can worry about mechanicals and other stuff. But what I'd like to bring up is the thing that I think most people are missing in this discussion, is it's not like the electrical interface, it's what's the protocol behind it. Because that is very different. Are you doing a coherent shared memory interface like CHI, or is it some kind of a streaming protocol? And so, we've looked at lots of opportunities where somebody, oh, they have exactly the interface we want. Oh, but it talks the wrong protocol, right? And so that's the kind of thing that's not often mentioned that I think is going to be a barrier. We need some standardization efforts there as well. But there's just so many of these individual standards and so many different groups who think they are leading and setting the standard that's why I think short term for the next year or two, there will be a lot of confusion until this settles out. And by no means do we know what the answer is today.
Go ahead, Chen.
No, I just want to say real quick that I also think like the hardware APIs that I was talking about, like all the management, power, telemetry, all those things, because these are the ways that software consumes the SoCs, right? So if we have 10 different ways to do power management within a SoC, I mean, I don't see how that happens, right? So I think that there is a lot of work that has to be done there, and how these technologies are consumed by the software itself. Because if that can be managed, there is no point on on the physical, because it won't be able to get productized.
Yeah.
So I would say that in addition to the compatibility, performance is important. Like when you look at across the different standards, right, you have UCI. Well, look at the throughput. Then look at Infinity Fabric from AMD, or the AIB, whatever, for Intel, and then Rambus. They all have such different things, right? Why are we doing chiplets? To get higher performance. If you get a really common denominator where you're losing in performance, that doesn't do you good. Where I think this will all land up is, I mean, again, I'm dating myself, right? So there was a time when every sort of system vendor, IBM, HP, Sun, everybody had their own processor, right? DEC Alpha, and so on. But the whole thing went for the Wintel architecture, right? That became a standard, right? So, and then essentially everybody started, well, AMD supported the x86. So I think it's going to go in that direction. I think right now everybody is jostling to be the standard. But I think unless something like a Wintel coming out, and then everybody signs up. But the most important thing is it's not just the compatibility, but the performance has to be there. Otherwise, the whole chiplet promise is gone.
Yeah. So quick question for you guys. You look at how things are going with people pushing different standards for chiplets, because they want to sell the chiplet interface as an IP, sort of. And so they're vested in keeping you into their ecosystem. Now, let's go back a couple of decades. ARM, a big pivotal moment, I believe, is when they made the interface between their IP components open so that anybody could use it, and you didn't have to buy into their ecosystem. I mean, you needed to buy into their ecosystem to get their cores, but third parties could also create IPs that would integrate. And ARM spent a lot of effort to ensure that it was truly Lego-like, but on a monolithic die. Is there anybody positioned right now that is going to be willing to make that open and not try to sell the IP, but actually say, I'm giving it away so that I can sell the chiplet?
I work for Ansys, but within 6 months, Ansys will be part of Synopsys. So my position is somewhat not very maybe it is biased, but I will still say, right? So you look at the EDA companies that are going to support this workflow, these Cadence, Synopsys, Siemens EDA. Those are the three big players, right? And each of these companies, they have an IP business. The largest IP business is, you mentioned, ARM is a separate category by itself, like $2 billion plus, right? But among the EDA companies, the largest IP business is Synopsys. And then there is Cadence. But so basically you take the different IP blocks that you need. You need HBM, you need PCI, you need WiMAX, right? So essentially there are IEEE standards, and each of these companies, Cadence, Synopsys, et cetera, they are creating IP blocks as SoC blocks to be used today with the same technology, right? And so this is a homogeneous thing, right? All on the TSMC's 2 nanometer technology. But it is possible to use that same chiplet idea, right? And so both Synopsys and Cadence have these workflows, UCIe based, that will allow you to do this. So I think it is the users, the developers of the IP, and the customers who will have to kind of work together, and that is how the standards will get resolved.
Okay.
And of course, I should add that the specific, what needs to be open is the specifications. Like, for example, what the signaling is.
And I spent 9 months getting an NDA to get an open specification. What the hell is that?
But that, I assume that has been the goal of UCIe, BOW, and solutions like other like D2D standards like that. But, and hopefully it will come together sooner. But I know it's been a while. BOW first started in 2018, and we're 2024. It's,
to me, standards need knowledge.
Yeah.
And knowledge do not come free either for time or experience or just we need data and we need knowledge to back up the data. And always in our packaging systems, it is the interface that's the toughest. In early days, we work on solder. And solder is the interface, and it is the weakest point. And people work on different solders, start with highlight in IBM, and then we go into different solders, then we go to the low temperature, et cetera. But each time when we do this, the knowledge base need to be invented. Need to be studied. Let me just give a simple case. Maybe about 10 years ago, ASC was the pioneering for copper wire bond. And in that copper wire bond, the bonding, it is the bonding interface that is the weakest. And then you have to have the science to develop the standard for people to inspect what is the strong interface before you can have a standard. And I recall long discussions on how to develop the standard in terms of you may call it failure analysis, or you may call it testing, to see that you've got an adequate interface. Now we are coming to the same situation. The hybrid bonding, how do we know what to put together as a standard unless all of us spend time and effort to develop that? Then you can put it into the modeling.
All right, I'm going to take a question from the audience here.
Yeah, so I see the need for standards at many layers, and I think you remember from my slide, I mean, the protocol is definitely one of them, but I actually wanted to go back for a minute to the physical layer, just because in thinking about designs, even the placement of the PHY makes a lot of difference. And I know UCIe has put standards about the shoreline, the bump patterns, and they've given recommendations for different bump pitch ranges. But even if I designed a chip and I put my phi over here, and you design a chip and you put your phi over there, that's going to increase the path length unless they're just sitting right opposite each other. And I'm just wondering if you could talk a little bit about maybe the process to getting some standardization, without having like a new sheriff in town or something that says, okay, everybody's going to do it like this. I mean, what do you see as the process for getting to some reasonable standards, given that putting chiplets together on a package is probably going to require a higher level of agreement and handshaking?
Mm-hmm.
I can say, at least being part of the BOW committee, and there were a lot of great guys that focus on this to address the issues that you're talking about. And part of the reason that we started with the standard packaging was the fact that in a standard package, you don't have the length limitation issue. And you go on an advanced package, silicon substrate, it's so lossy that you have to abut this, those chiplets together. But on a standard substrate, you can go 5, 10, 20 millimeters. So it gives you a lot of flexibility. You don't have to perfectly align things. The other things that the BOW committee did was basically what we called maybe configurable bidirectional ports, meaning each port has both a receiver and a transmitter connected to it. So you don't have to plan in advance that these ports are receive, these ports are transmit. So you put them there, and then afterwards, depending on what you're going to connect to, you select what ports are receive, what ports are transmit. And this gives you significant flexibility. Having said that, still, you can have a strange configuration that you cannot fit all the chiplets that you want to connect with together. And that's a challenge, I understand, and it comes with some of the limitation of chiplets, but at least I know industry has been working on it.
Mm-hmm.
So I would say, it's a great problem that you have identified, right? But the same issues happen for SoC designs, right? When you're taking IP blocks from different things and you're putting together on a chip, right? You have sort of similar issues because you can end up with a lot more interconnect layers and so on. So I go back to the 3 major EDA vendors like Synopsys, Cadence, Siemens EDA, like Mentor. And essentially, and in my slide, there was one quadrant that kind of showed the concept of co-design, co-simulation. So I think the answer to your question is that, right, as you're doing this, you cannot just do the design of the chiplet by itself, right? As you're doing it, you say, hey, you find this out, and therefore you co-design, and you kind of change the placement of those things so that the overall optimal thing is together. In the morning today, I just referred to a thing like, it's ultimately the customer that will define these things, right? So the person who is using those bunch of chiplets for their solution. So I was talking to one of the business presidents for Infineon, right? They are a large semiconductor thing for the automotive market, and they are into chiplets. Now, their angle of chiplets is not the homogeneous chiplets the way AMD, Apple is doing, right? As Dave was mentioning, but they want to take the best chiplet for this particular thing, which is a 28 nanometer stuff, right? Then they will take something which is 12 nanometers. So essentially taking different things. That is a real chiplet use case, right? In the automotive area where they're driving towards EV and AV and so on. So what I think is going to happen is in different industries, and I'm sorry, John, you had a question on it. I'm sort of answering that question because that was going to be my answer.
Yeah.
Depending on the industry verticals, right? So you pick, so in Ansys, we have verticals like automotive or aerospace and healthcare. Each of these verticals, people are thinking about the use of chiplets to drive it, but the real use case will be not chiplets using same 2 nanometer technology, but a chiplet having an IP block with 7 nanometer, another with 20 nanometer. You pick the best of those things because that is how you'll get the lowest cost and the highest performance designs.
So that leads to a question, is it, right now everybody's motivated, as Bill pointed out earlier, it's not free to get that knowledge, right? But we know that people have cracked it, but they need to get that money back that they invested. Is this something, because we really want to get to the making money in the chiplets and not on the decisions that were made, engineering decisions made to get that knowledge, should that be pre-competitive? And completely ignoring the government guy in the room, is that a role that the government could play in order to make this a pre-competitive investment to solve these engineering problems and share that knowledge rather than leaving it up to the marketplace to shoot it out?
I don't know. Usually when I want something to move faster, I don't say, can we please get the government involved? But on the other hand, I think you make a very valid point that this is going to take a lot of effort. And it's something that, so for example, the very largest companies, the Facebooks, Googles, others will have the capability to, put people on this and support it for multiple years in order to make this happen. So I think that's an issue. And I think we're going to need, some very large players to help force what I'm going to call the political solutions, right? Because to the naive audience, they say, well, guys, if standards are so important, why doesn't a bunch of wires and UCI just get together and, make a compromise and come up with one standard, right? And the marketplace will end up having to decide that, I think, is really what's going to happen. But it will take a long time, and we will need the support of government, large companies, everybody else, in order to get to a future where we translate our PowerPoint slides that we'll just take things out of a catalog and plug them together, and it will just automatically work. Right? So I think it's the right thing to push forward, and the question is, who can sponsor all of this going forward? Because it is very expensive with all the standards and everything we have to put into it.
No, I would say which government?
All of them.
Yeah, but that's the thing.
It's not
Glad to see the EU involved, right?
Yeah, exactly. I mean, I think that at the end, the economics should drive this, no? And I think that it's of interest of all the chiplet companies to drive this standardization, and I think it has to be on the technical and business side of the house, because otherwise, I mean, to Dave's point, it will take some time, but it's much better if there's consensus on how things get decided.
Bill?
You talk about pre-competitive. Now, the roadmap is pre-competitive. And how did roadmap get started? 1992. We have roadmap started in 197. Experts was invited to Irving, Texas, to work together and looking into the future of what are the information that can be shared, and how do we step by step develop the knowledge into the future. And I think that our heterogeneous integration roadmap is pre-competitive, so that we could all share the information, and we all make sure that when we discuss things together, we do not put our company's interest into those roadmaps.
Yeah, very good. All right, so last question, because we've got our 2-minute warning.
Yes, so I've worked in chip verification for quite a long time, and I would say that we've reached the limit of what we can do as humans, so bumping it up to chiplet systems and adding a lot more complexity. Do we have the tools to do that in the EDA companies? Is it time for a new set of tools and maybe open source tools and some AI to go with that?
That is a great question, thank you. You are absolutely right. We are coming to the point, that's kind of why I said that, again, at Ansys, we have verification tools at the physics level, but there's obviously simulation tools at multiple levels, as you know, right? But these systems are getting so complex that the runtimes of a truly accurate physics-based simulation is getting really limited, which is where, first of all, technologies like brute force HPC, by brute force I mean shared memory, message passing, GPUs, we have taken our solvers to run on not just one GPU, but those sort of Blackwell GPUs, I mean, the largest scale NVIDIA GPUs, so that you can have tremendous amount of compute to parallelize our fluent applications, right? And we are working on it. But even that is not enough, because the runtimes are getting to like the tens of thousands or hundreds of thousands of hours. That is where AI is coming to the rescue. But let me tell you, there's an AI phase 1 and there's AI phase 2. The AI phase 1, which Ansys and other companies are working on, is to take a black box solver, like Ansys Mechanical, give it an initial condition, boundary condition, like one CAD model, upload it, do the look at the output. Here is the input, here is the output, and you program your neural network, right? You do a second case, third case, you give it 100 cases, it learns the physics for those parameters of CAD, and then you give it a 101st design, it runs like a 1,000 times faster. We are at this point all together, right? So today we have a tool called SimAI that can do it, but that's for parameterized design. If you're doing a laptop which is this side, this side, this side, you change the things, right, with some parametric changes, right, which is all rectangular. You give it a circular thing, it has not seen it, so you cannot do it. Where this world is headed is foundational model for 3D physics, where you will not have to train it. The customer doesn't have to train it. You have trained it on billions of use cases, right? And where do those come from? From synthetic data. Well, you can actually run all those physics-based simulation, assuming gobs and gobs of compute and so on and so forth. Once you learn the physics, that is the real disruption that will disrupt the whole numerical methods market. We are not there yet. It will be at least 5-10 years before we do it, but that is the point where the simulation tools will be totally different. And there's a whole bunch of startups who are actually working on that technology.
Right.
But let me take you offline. Thank you.
Okay, great. And so, folks, we're at time. So I appreciate our panelists. Let's all give them a round of applause. And we've come to the end of the session without any injuries, so this is great. Thanks.